Hope everybody enjoyed this beautiful weather we had today. I don't know where you are, but here in North Carolina, it was fantastic outside. So hopefully you got out there and got the wrench on something or work on your favorite car. So we're just going to give everybody a few minutes here to get online. I don't have my tech crew with me today, so I don't know if this is going out or not. So hopefully you can see me. Hey everybody, I think there was a little bit of a glitch there, so hopefully you guys are seeing this clear now. Anyways, as always, if you can hear me, if you can see me, if everything's coming through fine, then give me a like, give me a thumbs up, something, give us a comment, let us know that you can see this okay. We're going to give it a few minutes here, like we normally do, to kind of let everybody get logged on and let this go out, and let everybody know that we're live. But appreciate you guys checking it out. If you're on Facebook or YouTube or wherever you're seeing this at, we do appreciate it. And like always, I say it every time, but we do want to try and make it as interactive as possible. So if you have questions, if you have comments or anything, feel free to put them in the comment section here, and we'll try and get to them live as they come through. I'd like to try that anyway. So shout out to Russell and Stephanie and Robert and all the O'Reilly crew. I'm wearing my O'Reilly shirt tonight, so shout out to you guys. Hope everything's going well where you're at. And again, like I said before, we had beautiful weather today, so hopefully you got to get out and do some wrenching, or at least do some cleaning up, or whatever the case. Hopefully you enjoyed the weather anyway. But yeah, tonight's lesson is called Broken, and really couldn't think of a better tie-in than broken, because anybody who's ever spent any amount of time in church or Sunday school or whatever the case is knows that we are broken people, and we're going to see that tonight. But also, cars break. That's what they do. Unfortunately, they're machines built by imperfect people. So we're going to see a little bit of that tonight. Again, like I said, I don't know if you caught it a little bit earlier, but give us a little thumbs up or a comment or something to let us know that you're online. I see there's a few people logging on here as we get started, so I think we'll go ahead and move forward. So, Smith's second law of motor racing. This is one of my favorite sayings in all of automotive engineering or mechanics or racing or anything. There are no truer words than this usually. This is written by Carroll Smith. He was a race car engineer in the 60s and 70s, and he's legendary for his race cars. But he wrote a book called Engineer to Win, and then in that book he says, there is no such thing as material failure. All failures are human in origin. And I don't think that could be more true. One of the things that he talks about in that book is that metal and materials, be it plastic, metal, whatever the case, doesn't think, doesn't have a mind of its own. And it's a person that designs it, machines it, installs it, maintains it, and uses it. And usually in one of those areas is a failure. And that's what causes failure, not necessarily the metal itself. So it's either improperly designed, improperly used, improperly installed, or improperly maintained is almost always the case. So along those lines, we're going to start with our first verse tonight, and it's Romans 3:10. It's a simple one, but it's very, very powerful. And again, this is something that I think speaks to all of us. I know myself very much included. But Romans 3:10 says, as it is written, there is no one righteous, not even one. And I think it's pretty clear right there is what he's saying. There is not one perfect person, not even one. There was one perfect person, but he is back up in heaven and looking out for us right now. But as far as us here on earth, there is no one righteous. And like I said, that basically means that there are no perfect people. And as we're going to talk about, there are no perfect machines either. Psalm 147, 3-6. I thought this one was really good too. He heals the brokenhearted and binds up their wounds. He determines the number of the stars and calls them each by name. Great is our Lord and mighty in his power. His understanding has no limit. The Lord sustains the humble, but casts the wicked to the ground. And I know that's kind of a mouthful, but I wanted to definitely include this one in our lesson tonight, because it talks about how he's a healer. He heals the brokenhearted. He binds up their wounds. This is showing God's power knows no limits. His understanding knows no limits. And again, this is something we're going to find out later in the lesson, that our understanding definitely has limits. But I also included verse 6 right here, which I didn't have in the original one, but the Lord sustains the humble and casts wicked to the ground. And I really like that because, again, when you think you know everything or when you don't think there's anything else you can learn, that's a pretty dangerous place to be. So we need to stay humble. We need to stay humble in all areas of our life, but definitely in this particular area. So that's one I definitely wanted to include. In Ephesians 2, 8 and 9, for it is by grace you have been saved through faith, and this is not from yourselves. It is the gift of God, not by works, so that no one can boast. And I think a lot of people have probably read this verse several times, and I know, it's something that I see in Sunday school, I see in Sunday sermons and that sort of thing. But this is another one that is short and powerful and to the point. It is by grace you have been saved through faith. So it's nothing that you can do. No works, no amount of charitable giving or Sunday school attendance or even watching these videos is not going to save you. It is strictly God's grace that has saved us, and I think that is a very, very powerful message, because if it were up to us, if it were just us to do good things and to do good works in order to be saved, I think there would be a lot more lost people out there. So, and I like right here, he says, but not by works, so that no one can boast. So in other words, some people are better at some things than others. So if there was a certain thing that you could do to be saved, then those people could boast, right? They were better at it. They did it, whatever it was that needed to be done. But in this case, it says it's specifically designed that way so that no person can boast. It is strictly by grace from God. So I just thought that was a really good one too. In this, again, talking about us being broken people, the title of our lesson tonight is Broken. This is one that I really, really wanted to include, and I think this probably drives the point home. But 2 Corinthians 12, 9 through 10. But he said to me, and this is Jesus speaking to Paul, my grace is sufficient for you, for my power is made perfect in weakness. Therefore, I will boast all the more gladly about my weaknesses, so that Christ's power may rest on me. That is why, for Christ's sake, I delight in weaknesses, in insults, in hardships, in persecutions, in difficulties. For when I am weak, then I am strong. And again, this is one of those ones that I think really speaks to me personally. I mean, this is one that I need to work on. And, if you're out there and, this really kind of hit home with you, don't feel alone on that, because this is one where he's delighting in his hardships. He's delighting in his weaknesses, in his insults, hardships, persecutions. And Paul had a pretty rough way to go. I mean, if you read the Bible, he went through some pretty tough stuff, and in all of that, he did nothing but praise God. And this is one of those examples that he's saying he's happy. He's happy when those things happen to him, because that just means God's power, Jesus' strength, is made all the more apparent. And I wouldn't be talking to you right now on Facebook Live if it wasn't for some pretty hard things going on right now. And I think there are pastors preaching sermons on this probably all over the country right now. But there are definitely some hardships. There's definitely some trials. But again, there's a lot of really good things going on. You're spending more time with family. You're, making more home-cooked meals, or you just get a break from whatever high-stress job you might be in. So there's a lot of things that you can look at and say, it's been really good. I mean, my views on this class have gone through the roof, and I think a lot of that has to do with people staying at home. So, if this is reaching more people because this is the way we need to do it, then, hey, that's praise be to Jesus for that. But this is another one talking about, we are weak. We do face weaknesses and hardships and persecutions and difficulties. And so in those things, we just need to remember that it's in those weaknesses that his strength shows through. So with that being said, one of the tie-ins here that I really wanted to get across, and hopefully again, this makes sense to you guys as I wrote it, but designed to a price. So everything that you probably handle, this phone, this computer, this TV, your car, your washing machine, your refrigerator, whatever it is, anything that you buy is typically designed to a price point. I think we could all agree with that. There are some things that cost not as much, and some that are very, very expensive for what appear to be the same thing, right? I mean, you could buy a refrigerator for $600 or $700, or you could buy a refrigerator for $2,500 to $3,000 probably. And both of those things will probably keep your food cold, and that sort of thing. But why is there a giant difference? It's because the components and pieces and parts in it were designed to a price point. There are different quality levels of pretty much everything, and cars are no exception. But I wanted to tie this into what we're talking about, in that just as all parts, pieces, and components in a vehicle are designed to a price point, so are we. God has engineered and built each and every one of us perfectly for the price of his Son, Jesus Christ. Jesus gave his life so that we would not have to pay the price for our brokenness as long as we accept him as our Savior. And that really speaks to me because, you might think that something is really, really expensive. Let's use a car, for example. Maybe 60, 70, 80, 100, 150, or even, $1 million is a lot for a car. But that's really nothing compared to the price of Jesus's life, right? I mean, I would hope that you wouldn't think $100,000 is worth someone's life. And that is the price that we've been built to. So you think of the most expensive car out there and the price point that it was built to, and target market, who they planned on buying that car. Well, Jesus was the price for us. And I think that's a really powerful statement. I think, we do good to keep that in mind, that we were built to that price. So let's talk about some failures. And as we get into the more technical side of the lesson here, again, I see we've got some people going in and out. So, say hey, drop a comment, drop a like. Let me make sure that I can see you guys, because again, I don't have Zach on his phone over here tonight to let me know. So go ahead and let me know that you guys can see this. All right, cool. There's Ronnie Walters. Man, good to see you, buddy. And again, we're going to kind of get into the weeds a little bit. If you've watched any of these other videos, we do get kind of in the weeds. We do get a little bit technical, and I don't expect that everybody out there is going to be a professional technician or do this for a living. I would hope not. I'd be out of work, so appreciate you guys. But what I would like is maybe give you an idea of what it is that fails, why it fails, and maybe when you do talk to a professional, or you do go to a shop, or you go to a parts store, whatever the case is, maybe you'll be able to understand a little bit and relate back and forth, and you guys can communicate a little clearer on what it is that's actually going on. Because, on both sides, on the mechanic side and on the customer side, if we understand each other, then it makes everyone's life a whole lot easier. Hey, David, what's up, buddy? Good. I'm glad you guys are getting this loud and clear. Thank you. So we'll talk about some types of failure. We got thermal, which is temperature, heat. In most cases, unless you live in some extreme cold places, there are some really, really extreme cold failures that can happen on cars. But most of the time, it's heat. Material fatigue. Physical, like damaged components. You run into a curb and break your wheel. That's a physical failure. Electrical failures, which we're going to spend quite a bit of time on, because anybody who knows me knows that that's my favorite thing to do. I work at a shop that does mostly electrical diagnosis and repair, so that's what I spend a lot of my time on. Abuse, so basically beating it. You go to get groceries in your Camry and you're banging it off the rev limiter and, spinning tires all the time. I would call that abuse. And then design and manufacture. So this is a failure of design or the actual manufacturer of the component. So either it was designed incorrectly, or, the engineers gave the manufacturing plant the plans and they just did not build it correctly. But we're going to talk about a few of these. We're not going to go all over in all of them in detail. But I just want to give you an idea that most of the time, a component failure can be categorized in one of these categories. So we'll talk about material fatigue first. And again, I hope you guys can see this. If not, I'll post the link to these slides online so you can check them out later. But I'll give you a little bit of a rundown here. Metal fatigue. In material science, fatigue is the process by which a material is slowly and progressively, and oftentimes permanently, damaged by stresses and strains that are less than those needed to actually break the material apart. So I'm going to stop right there, first sentence, and just kind of broad overview. If you have a material that has a certain amount of stress that it can take, a metal, for instance, aluminum or plastic or whatever the case is, it would take a certain amount of force or a certain amount of strain to break that material. But over time, those stresses and strains can add up, and actually the material can fail at a point less than the stress actually needed to break it. Kind of like bending a coat hanger back and forth. You bend a coat hanger back and forth a whole bunch of times, eventually it breaks. Well, the amount it took to break it was less than what it would take to actually break the metal the coat hangers out of. And the reason being is because you fatigue the metal. You actually stress it to the point that it fails at a very low point. Over time, these weights slowly cause defects to develop in the metal, and these defects might occur as scratches, notches, particle formation, or other abnormalities. And at some point, these defects become so great that the wire or steel actually breaks apart, even though its tensile strength had never been exceeded. So, kind of what I was talking about right there. That's where it can actually fail at a point less than it was designed to handle. And you see this, airplanes, race cars, that kind of thing. It's very important that they deal with fatigue. They usually have a schedule, where they replace certain parts based on hours and use, because they want to replace that part before it fails. Obviously, if your car breaks down on the highway, that's an inconvenience and maybe an embarrassment. If a plane breaks or a race car breaks, now you're talking loss of life and a huge big disaster. So it's very important that they usually replace components based on hours in use and not thousands and thousands and thousands of miles. Nerd alert! I had to put this in here. So for some of you out there, this formula may mean something to you. For most of us, including myself, that's not something we really deal with very often. But I wanted to include it just because give you an idea. So the coefficient of linear thermal expansion, and basically what that is saying is that different materials expand at different rates when heated. And I've left a couple of them down here. I don't know if you can see those or not, but I've got aluminum, stainless steel, and cast iron. So aluminum has a expansion coefficient of 21 to 24. Stainless steel, 304 stainless steel anyway, is 17.3, and cast iron is 10.4 to 11. Now, what those numbers mean basically is that if you were to heat aluminum, stainless steel, and cast iron up to the same temperature, the aluminum would grow quite a bit more than the stainless steel, and the stainless steel would be more than the cast iron, and the cast iron would be the least out of those. Now, why does that matter? Well, as most of you all know, that car parts, and most all of them, get extremely hot, and then they cool down, and then they get extremely hot again, and they go through these cycles constantly over the life of the car. Well, aluminum, stainless steel, and cast iron are three very common materials used in automobiles. And these things expand and contract at different rates. And so auto manufacturers have to account for this. If you've ever seen aluminum heads on an iron block, or cast iron manifolds on an aluminum head, or so on and so forth, they are expanding and contracting at different rates. And so the manufacturers have to account for this. And that expansion and contraction over time can add to metal fatigue, just like bending that coat hanger back and forth. So metal is not the only thing that can fatigue. Plastic and rubber can fatigue as well. And these are some real world examples. These are actually pictures. These are some stuff that I've dealt with. In fact, that radiator was out on one of my personal vehicles a few years ago. But in these cases, you see here this radiator, there's a chunk missing out of it, and it's split down the seam. This is a timing belt. I don't know if you can see, but there's a timing gear, and there's a broke off belt right there. That's a rubber belt that's just failed because of fatigue. There was no actual physical damage to that belt, just like that radiator. Nothing actually, flew up and hit it, or, there was no damage to it. And same thing with this infamous Ford intake. If any of you guys out there ever dealt with the 4.6 liter Ford intakes, Crown Vic, Ford trucks, that kind of thing, Mustangs, they were infamous to split and leak coolant. And there's actually three places that they were pretty infamous to split. But this is one of the first plastic intakes that was used widespread. And Ford just didn't account for the fatigue in these particular areas. And what we ended up seeing was failure. And they would fail without warning most of the time. So you'd be driving along just fine one day, and then next day you go to start your car and all the coolant is dumped out. Because that last thermal cycle, that last heating and cooling, was the straw that broke the camel's back. And it pushed it over the edge, and it allowed it to split. So metal is not the only thing that can fatigue. Rubber and plastic can also. But we're going to talk a little bit more about why that is in just a little bit. This is a connecting rod. And again, this was probably more of a abuse type situation than fatigue. But it does show you how what appears to be a very, very solid piece of material. This is an iron rod, probably forged, I would guess, or cast of some type. I don't know. But usually these are very substantial. and you can see it's just broke right in half. Now, usually when you see this, it's an over RPM situation, or somebody shoved a bunch of boost or nitrous through it, or something of that nature. But you can see that that's a pretty substantial piece of material. That's a pretty heavy piece of metal, and it can just break and fly apart. Just kind of give you a little overview right there of what we're looking at. But yeah, that is broke slam in half, and likely windowed the block of whatever the engine that came out of. So it's not a good situation. But this can also be caused by fatigue, because the compressive and stretching forces that these rods go through is immense, especially as RPM increases. The higher the RPM, the higher the loads that are put on the connecting rods. So that's why, you see big, giant, 400 plus cubic inch engines, diesels and that kind of thing. They usually don't rev really high. And then you've got little tiny, 4 cylinders, 2 liters that will rev to, 6, 7, 8, 9,000 RPM in some cases. Rods play a huge part in that. The rod weight, the rod length, the rod design, that kind of thing. But yeah, they try to keep the RPMs down on cast rod stuff. But let's talk about electrical failures for a little bit, because I want to spend the most amount of time on this, most likely. This is one of the things that I see a lot in my shop, and if any of you guys out there are professional technicians, you probably see a lot of this too. But what I want to do is talk to the average consumer, because this is one of those things where it's most often not the part that's broken that caused the failure. There's usually some other cause there, and we'll talk a little bit about why in just a minute. But current protection. So when we're dealing with electricity, when we're dealing with automotive electricity anyway, we were really trying to control current. We're really trying to control amperage. And, there are some things on the car that are really, really high current, and there's some that are very, very, very low current. And we try to keep those separated, obviously. But we need to protect those components and those wires and that sort of thing. And usually we do that with fuses. Most electrical failures can be traced to a high current draw in the circuit caused by high resistance, shorted wires, failing components, such as injector coils or blower motors. When the load is high, current increases, creating heat. Heat is the enemy. We've talked about that in the last class. We did a little bit of a cooling system type deal, and we talked about heat and heat exchangers and that kind of thing a little bit more. But heat is the enemy in everything. It's the enemy in coolant. It's the enemy in transmission fluid. It's the enemy in electrical systems, obviously. And here we've got fuses. That's the most common sort of current protection that cars use. These are rated to a certain amperage, and when that amperage is exceeded, the little metal strip inside of the fuse opens up and stops current flow. That's why it's very, very important not to put the wrong size fuse in a spot designed for another size. Because let's say that was a 10 amp fuse and you stuck a 30 amp in it. Well, the fuse blew, so there's obviously a problem. There's a short somewhere. There's a component drawing too much current. There's some reason that fuse blew. They have no moving parts. They very rarely, if ever, just fail to be failing. So if you were to stick a 30 amp fuse in there, now 30 amps can travel through that circuit instead of the 10 that it was designed for. And now you can melt wires, you can melt connectors, you could actually damage components. In extreme cases, you can cause fire. So you definitely want the fuse to be low enough to open up if there is an excess current. And like I said, every circuit has its own designation. So make sure that you always put the correct fuse size back in its hole. Don't just pull any old fuse out and stick it in there. Or like in the old days, wrap a bubblegum wrapper or something like that, or paper clip or whatever, and stick in there. Don't do that either. Relays are another way that we control current. And what these really are is it's allowing us to switch a high current circuit with a low current one. So the best way I can explain that is, let's say your headlights on your car, if you've got a relatively modern car, they can pull a pretty substantial amount of current. But your little headlight switch on your stock uses very, very tiny wires and a very, very light switch. So how do they get all that current to go to the headlights with that little tiny switch and those little tiny wires? They do it with a relay. And what it is actually got a magnet inside, or a coil, electromagnet, and a actual physical piece of metal that is acted on by that electromagnet. And when you switch the magnetic field through here, it actually pulls down on the metal strip and allows high current to flow without ever touching the low current side. So it's actually acting as a switch. It's opening and closing this high current circuit based on current flowing through this electromagnetic switch. It actually is a coil inside of there. If you ever seen a relay, it's a little square box and it's got a little coil in it. And when you apply current through that coil, it creates a magnetic field. It pulls down on that metal strip and it allows high current to flow through it. That way we can switch really, really high current devices, blower motors and headlights and starter relays and all that sort of thing with a relatively low current switch side. Most modern cars nowadays are using what they call IPDMs, and they work similarly. There's no moving parts inside of them. They use FETs or field effect transistors, but they're able to limit current using solid state devices. So they actually have a module inside there that can monitor the current on a circuit and shut that circuit down if it deems that there is too much current on it. Most all cars are going to this nowadays. That's why if you see like Ford trucks are a really good example of this. You get a headlight out or a tail light out or a brake light out or anything like that, and you get a message on the dash that says, left tail light out or something like that. That's how it knows, because it's monitoring the current on that circuit, and it says, hey, there's no current being used by that circuit, so you must have a problem, and it'll give you a message. And if there is a problem, if there is a short, it can shut it down. Well, you go and replace the bulb, and still doesn't work. Well, a lot of times you actually have to go in with a scan tool, with a computer, and clear the codes in these things before they'll come back to working. So yeah, I've seen that a bunch of times. A customer says, hey, I put a bulb in it and it still doesn't work. And I go in there, I clear the codes out of the IPDM, and it goes back to working. And it does that. It's a self-protection device. It's doing that to protect itself from an overcurrent situation, because there are no actual relays inside there. It's all solid state. So that is one example of what most modern cars are using nowadays. But the fuses and the relays are still being used in quite a bit also. So we keep talking about current. We keep talking about high current. Now, what are the downsides of that? Well, high current equals high heat. And these are some examples of connectors. Some of you guys have probably seen this before on headlights, DRLs on Chevy trucks, headlight switches on Ford trucks and that kind of thing. BMW headlights, they're pretty notorious for this. So what you see here is you actually see burning. You actually see kind of a charred look. That's melted the plastic. It's burnt the terminal. In this case, it's actually melted the insulation back. This one you see is actually melted out of the plastic. This is a headlight one. This is very, very common. You see in headlights and that sort of thing, especially in GM trucks, BMWs, Mercedes, that kind of stuff. You see that a lot. But the deal here is heat. Heat has burnt all these connectors. And why did they do that? There's a lot of theories out there. Headlights are different than they used to be and such as that. But the main thing is it's usually a high resistance issue. It's usually a loose connection. And when I say loose, I don't mean like, it's actually shaky. I mean loose on a very, very small scale. These pins will actually get bent from heat. They'll actually move around because they get hot and cold. Moisture can get inside here and cause corrosion, which will actually make the connection, not as good. And a lot of times what happens is this takes a long time to take place. It's not like, they just burn up overnight. And although they can, but usually it's happening over time. And as that current is higher and higher and higher, because this connection is looser and looser and looser, it actually creates so much heat that it melts these connectors. This is why it's important that, if you go to the parts store and you buy some headlights or you buy, some electrical component, they usually try to sell you a little pack of dielectric grease, right? If you're a professional tech, you probably have a tube of it, a big tub of it sitting on your toolbox. But that grease, that bulb grease, some people call it, dielectric grease, it's like what you put on spark plug boots, that kind of thing. It's extremely important. And in these cases, these ones are too far gone. They have to be replaced, at the wire and a new connector or whatever. But when you're replacing bulbs, it's important that you do that. And the reason being is because that grease does not conduct electricity, but it does keep moisture and air from getting to these terminals. And, we all know that oxygen and moisture is corrosion. So you want to definitely put those on any high current devices, and especially light bulbs, because light bulbs, they get hot anyway. And most of these connectors live under the hood where it's extremely hot also. Another place where we see this a lot is high current DC motors. And most people will be surprised to learn that cars are full of high current DC motors. The examples that I've used here, we got a blower motor, like your air conditioner blower motor or your heater blower motor. Your starter motor, that's extremely high current. That's 200-300 amps DC motor. We got a wiper motor here. Windshield wipers. That's another high current area. Windows, power window motors. I don't know if they still build cars with crank windows or not, but just about everything has power windows. That's pretty high current. Fuel pumps. That's a high current DC motor that most people overlook. And electric cooling fans, of course, is another example. Now, there are others, your power seat motors and that kind of thing. If you've got a deck lid that raises and lowers by itself, chances are it's probably got a high current motor in it. But a lot of these, most all cars have these right here: cooling fan, starter, wipers, power windows, fuel pump, and blower motor. Now, what you see with a lot of these, and we're going to see some examples just like those connectors that were melted, is it's an overcurrent issue that causes the failure. Now, and a lot of times it can be, just like with the headlights or anything under the hood, it could be a corrosion or a loose connection that will eventually burn up the connector. But in these cases, a lot of times what you see is a physical, as something stopping the motor. It's a physical thing that is keeping it from turning. And if you were to try and stop this motor, then the amperage is going to go up because it's going to try and turn. And as you try and stop it, it's going to keep ramping the amps up until it either burns itself up or it moves whatever is holding it. And in many of these cases, fuel pumps, if you got a stopped up sock in your tank, you got a bunch of rust and dust and all kinds of crud in the tank, it's pulling against that. And the harder it pulls against that, the more amps it will pull. And you'll see the connectors on the top of these get melted, or the top of your fuel tank get melted. Same thing with wipers. Your wipers are froze to your windshield, and you turn them on, and it is pulling a whole lot of current to try and break those things free. Cooling fans, another good example. They live out under the hood. They get hot, they get cold, they get salt and water and all kinds of other stuff on them. And so corrosion actually builds up inside the motor, and it becomes harder and harder to turn, and you end up with a high current situation, melting plugs and that sort of deal. Blower motors. I've seen plenty of these with, McDonald's straws stuck in them, popsicle sticks, napkins that get, sucked off the dash, or, crap that's in your passenger floorboard gets sucked into the blower motor. Or another one that everybody ignores is your cabin air filter. And I know it sounds kind of crazy, but you can actually end up with a very, very expensive blower motor repair bill because the cabin air filter got neglected. And this had to suck against it or blow through it while it was all packed up full of dirt and leaves and who knows what else. And you end up with a high current situation on the blower motor. And a lot of times that will manifest itself in a bad blower motor resistor. And this is one of the things that I wanted to talk about. So in any of these cases, you could see a blown fuse. In the blower motor case, you could see a melted blower motor resistor or a melted connector at the blower motor resistor. Fuel pump, you could see a fuel pump relay or the FET inside the IPDM that is damaged. You could even see melted wires sometimes, especially with the starters. Starters pull too many amps. You see them actually physically smoke at the ends of the terminals. And a lot of these times you think, okay, well, that component's bad. And so you just replace the component that you can see is failed. Well, the problem is there's a reason that component failed. If that blower motor resistor is melted, or if it's failed and you see the connectors melted, and the technician comes out and says, hey, I recommend you put a blower motor in it as well because, that's very likely where the amp draw came from that killed this resistor. 9 times out of 10, he is not trying to just sell you extra parts. This is one of those things where, there's a cause and effect, and you don't want to treat the symptom, you want to treat the cause. So yes, the blower motor might have been working fine. You might have said, hey, I just had it on yesterday and it was blowing fine. And, now today this is burned up. Well, that can be very true. And it could still turn and still move air. But the amount of amps that it's drawing are far more than what it was designed to, at least the circuit was designed to. Same thing with any of these components. In most cases, if you see a failure, in the power supply of one of these circuits, it's likely either, a component failure behind it, or you have some sort of loose connection or a physical impediment. You have something physically keeping one of these from turning. That's just something to keep in mind. Another way to prevent connector failures, and this is one of my pet peeves, and so you guys are going to have to bear with me on this. But what we just talked about with the connectors that you saw melted and the components that draw a lot of amps. We want to try and prevent that, right? I mean, we're imperfect people and these are imperfect machines, but we want to try and do it as best we can to prevent these things. And tight electrical connectors are a must. You're working on your car and you take the screwdriver to it, you pop, you break the connector and you just stick it back on there and you're like, it's good enough. That can become a major problem because as that connector gets hot and cold, hot and cold, hot and cold, the connection inside of it is actually going to loosen up and you're actually going to introduce a chance for corrosion to take over, and you'll see that heat build up there. Clean, corrosion-free splices. This is another one. We all add stuff to our cars sometimes. You add a radio, you add some lights to the front, you add, whatever the case is. These splices need to be clean, corrosion-free, and weatherproof as much as you can make them. And we're going to talk about that in just a minute. Preventing and or clearing mechanical obstructions. This is what I was talking about with fuel pumps. You want to make sure that the sock is clean, that there's nothing inside the tank, that the fuel filter is not neglected. With blower motors, the cabin air filter is not neglected. You want to make sure that you not get straw paper and stuff down inside the blower motor. Your windows, power windows, you don't want to put anything in front of them. Those vent shades or whatever the case is, you don't want anything blocking off the movement of that motor. And alignment can actually be a big part of those motors too. Some cars you can adjust the window alignment on, and if they're too tight one way or the other, then it's a lot of resistance going up or going down. So that's something to keep in mind. And you want to put dielectric grease on all high current connectors. We talked about that with the headlights. That is very, very important. So, listen to your parts guide next time you're down there. Go ahead and get some of that. So what is this big red circle right here? These are not the way that you want to splice wires. And I've got some examples here in just a minute of what I've seen personally. But, these are not what you want to do when it comes to clean and corrosion-free splices. So what I've got here is Scotch blocks. Or tap cons, some people call them. Those are little plastic things. You stick the wire in, you squeeze them with pliers, and they send them down the road. I couldn't tell you how many failures I've seen in place of these. These are not even allowed in my shop. I don't even want to talk about them. The problem with these is that they're not weatherproof in any way. Water, moisture, dirt, anything can just get inside there and get to where the bare wire is. The part that actually contacts the wire is very, very small. And it actually slits the insulation of the wire in order to make contact. So now you've ended up opening up the wire insulation, and you've got a very, very small contact point. So that means you're trying to carry all that load through that very tiny little tab inside of this connector. And of course, they're subject to vibration because there's nothing preventing them from moving around. The wire's just flopping inside there. Wire nuts, these might be great for your house. I'm not a house electrician, but I know you see these in house electricity a lot. These have no place on a car, no place. They're not waterproof. They're not vibration resistant. Your car doesn't go down the road at 80 miles an hour and doesn't have to, see 400 degree underhood temps and 20 degree, startups and that kind of thing. These have no place on a car, so don't mess with them. This is another big one. These fuse taps. I don't know. Hopefully you guys haven't used these, but if you have used these are a big problem. And if you can't see that, what it is the actual little metal strip that goes around a fuse, and you tap into the top of it, to add on your circuit, add on your lights or your radio or whatever it is that you're adding on. There are a couple major problems with this. So one is it actually affects the way that the fuse fits in the box. So you have a physical looseness there. That you could actually create by bending the pins inside there because you're adding something to it. So you can actually create looseness in there that will burn the box. And two, most people don't pay attention to which side of the fuse they put this on. So every fuse has got a power side and a load side. So the power side is where the car is feeding power into that fuse all the time, usually from the battery or from some sort of junction box or something of that nature. And then the load side is the side actually going out to the component that's being protected. If you were to put this TapCon on the side that's hot all the time, and this wire, if you have some sort of failure, the component fails, or the wire gets rubbed through, or there's a short for any reason, well, now the fuse isn't going to blow. Now, whatever that is you added on, it becomes the fuse. So now, you've got a little 10 gauge wire running your amp, and it lays on the exhaust or gets pinched in the door jamb or whatever the case. Now you got a fire on your hands. because this circuit is no longer protected. You are actually using the wire as the fuse, and that's never good. And then I put tape up here. Now, tape is not in and of itself a bad deal. I'll use the electrical tape on occasion, usually to cover wiring harness or to try and hold on some wiring loom. But what I see a lot of is people just twisting wires together and putting tape over. That is not a good deal. That does not buy into our clean and corrosion-free splice situation. A couple problems with that. When you just twist a wire together, there's no mechanical connection, so there's nothing holding those wires physically together. And I know they feel tight when you twist them, but there's vibration, there's heat, there's cold. These things move around. They are metal, and also tape is not weatherproof. It's got moisture can get through it. So yes, if you want to use it to hold a bundle of wires or put some loom over some wires and hold the ends so that they don't slip around, that's all fine and good, but it does not have a place in making an actual splice. So let's talk about proper wire splicing. Since we're on the subject anyway, this is one of my biggest pet peeves, and so I told you I was going to spend a little more time on this. Always use the correct size splice for the wire size you are dealing with. And always use the correct crimping tool for the type of splice or the type of connector that you're dealing with. So I put 3 examples up here, and these are probably 3 of the most common butt connectors that you see. The regular insulated, non-heat shrink, just plain Jane butt connector, which I'm not really a fan of, honestly. But if you got no other choice, that's better than the other 4 options that we just talked about. Then we got the heat shrink built-in type butt connectors, and these are fine as long as you make sure that you get the wire all the way into the barrel, you use the correct type crimping tool, and you actually crimp the metal inside of there and not just the plastic on the ends. That's a big thing I see. They use the right kind of connector, but they don't crimp them properly. And then this is the type that I use almost exclusively. This is a non-insulated barrel type connector. These are great because you can actually see how much of the wire is going into the connector. You can actually see that you have a good proper crimp after you're done. And then you slide heat shrink over it and you heat shrink that down and it makes it completely weather tight, and there's no problems there. This is an example of using a non-insulated barrel type connector. I hope you guys can see that. This is done with the correct type of tool. You see it's got a little indent on each side, and it's had heat shrink placed over the whole thing and shrunk down until the glue has come out of the heat shrink on both sides, and that is a proper weather tight splice. There's no way that you can pull those 2 wires apart. There's no way that water and corrosion could get inside of it. It's small. It's easy to tuck back into the harness or whatever you need to do. But these are that's the correct way to do a splice. Now, they do have open barrel splices as well, which are also, they work just as well. They work awesome. In some applications, that's actually a better solution, but they look just like this, except they're shaped like a U, and they use a special W-shaped crimping tool. You usually see that on into battery cables and that kind of thing. But those are totally fine also, just so long as they get covered up properly. Heat shrink covering is a must when using non-insulated connectors, and it is highly recommended to use on all splices or connections to prevent moisture intrusion and corrosion. So even if you're using the, parts store special $1.99 butt connectors, if that's all you can get your hands on, and you've got the proper crimping tool, you crimp them, it is still a good idea to cover them with heat shrink, even if no matter what you're using it on, because you do not want water and moisture and things to get inside there where that bare wire is. And we're going to see quite a few examples of why that's a big deal here in just a second. And so there are also, as opposed to connector failures, which we saw, and we saw some wiring failure, you can have high current component failure. Now, in this example, we've got some ignition coils here, and ignition coils, are extremely high voltage, they're extremely high current, and you can see that these ones are slam, blowed out, burn up. 9 times out of 10, you don't see them failed quite to that degree, but they can fail, and a lot of times they'll fail internally, or you may see some heat damage at the top of them. These ones are extremely failed. But what we've got going on here is another indication of high current, and a lot of times this is caused by spark plugs. So you've got a misfire, and you say, hey, it's cylinder number 3 misfire, and the coil's no good. So you go down to the parts store, you get you a coil, and you stab it in. Well, once you stab that coil in, it may work for some time, but there's a reason that that coil failed most of the time. And most of the time, the reason that coil failed is spark plug wear. As the spark plugs wear, the gap increases, and the current that it takes to actually jump across that gap becomes greater. So the more stress we put on this coil to try and jump the gap on that wore out spark plug, the more heat is built up inside of this coil, and usually ends up being component failure inside the driver. Now, in this case, it's an extreme case where the spark actually blew out the side. But the point is, again, this is one of those instances where you want to treat the root cause and not just the symptom. The symptom is a failed coil, but why did the coil fail? And, I've seen coils fail for all sorts of reasons. You could have poor grounds, causes high current. You can have failed PCMs that drive them, 100%, that kind of thing. There are a number of reasons that they fail, but this is one of those situations where you might want to ask your technician, why did it fail? Or, if he comes to you and says, hey, this has failed, but this is what I want to do. I want to put spark plugs in it since you had a coil failure. This is one of those times that you can have a conversation with him, and hopefully you guys will be on the same page. Same deal goes with the PCM. This is an engine computer. I forget what this is out of. I took this picture, actually. But you can see here, I think this is out of a Ford truck, actually, but I don't remember. You can see here this component is completely smoked. I hope you can see that on the screen. But it is burnt slam up. It looks like there's been a fire inside there, actually. But a lot of times when you see something like this, especially inside a PCM, it's usually one of the high current components that has failed. An injector or a coil. That's two of the main high current components that PCMs drive. And this is another indication that, there's probably another problem. If you open up a PCM or you have a PCM and it looks like this inside, I would really start looking at the high current components. I would make sure that an injector is not shorted together, or a wire is not pinched, or there's not some other reason for this thing to have done that. Because again, this is one of those situations. Ford Escapes are a good example of this. You'll have a PCM failure because one of the coils is shorted inside. And one of the coils is shorted inside because the spark plugs probably went 200,000 without being changed. And so you get this domino effect where the coil shorts, and now it pulls down the high current driver in the PCM, and it burns inside of the PCM up. You buy a new PCM, you plug it in, you start the truck up, and guess what? It fries it too. Ask me how I know. But this is one of those cause and effect deals as well, where you don't want to just take care of the symptom. You want to try and get to the root cause of it. And again, like I said in the beginning of this, not everybody out there is going to do this. Not everybody is going to get this in depth in their driveway or become a professional technician, although I hope more of you do. But what this, I hope, does is maybe give you a little bit better understanding of why, technician might recommend a certain part, or the parts store guy might recommend a certain, add-on or something to go with it. Because most of the time that, there is a reason behind these types of failures. And then we've got some thermal failures. I want to talk about this for just a bit. Underhood temperatures have risen due to the increased use of turbocharging and packaging demands on the OE manufacturers. Average underhood temps range from 250 degrees to over 390 degrees in some turbo applications. That's 390 degrees Fahrenheit. That is extremely hot. Modern plastics, rubbers, and electrical components must be designed to handle the extreme thermal cycling. So they need to be able to handle that hot and that cold. And I'll put these pictures up here just to touch on this for a minute. There's not much we can do about thermal cycling. There's not much we can do about underhood temps in most cases, unless you're building some kind of hot rod car and you're changing things. You may want to take underhood temps into consideration, add some vents, add some, make sure your fans, make sure the hood, vents and that kind of thing are where they need to be. But I added these because a lot of times what I'll see is that somebody has done some sort of repair. They've taken the intake off, they put a transmission in it, they've done some sort of repair. And it could be other shops too, not just individuals, but they'll leave these things off. They'll leave the sleeving off the wiring harness or off some of the hoses, or they'll leave the heat shield off the exhaust manifold because it was a pain to get out, or because the bolts broke off in it, or maybe just didn't like the way it looked, or for whatever reason. Starters are another good example. That heat shield on the starter can be a real pain to deal with sometimes, and so sometimes people just leave them off. Well, that's when you can run into problems. Like we were saying, they can reach over 390 degrees inside the engine compartment, and these things were designed with these measures in place just for that. So, you leave the heat shield off, and then 2 weeks later, you've got some sort of wiring harness failure because it's burned up, or you leave leave the sleeving off of a harness or off of a fuel hose or something like that, and it melts and it fails, and now you've got real problems. So this is one of those things, just like the looms, the OEs put all the wiring harnesses in nice little looms and clips. They do that for a reason. And so if you do take something apart, try and make sure that you put all these components back into place and make sure you put the wiring back into their clips and their looms as best as possible. Sometimes they just crumble and they break, and you might need to reroute them or use zip ties or whatever you got to do. But it's very often that I see where somebody has fixed one component, like I said, maybe they did spark plugs, and then the car, comes to me with a harness melted from laying on the EGR tube because they didn't put it back in the lube, or maybe they put a starter on it and they say, "Hey, my starter fails every 6 months. There's something electrically wrong with this car." Well, the starter fails every 6 months because in those 6 months they're cooking all the new ones. So that's just something to keep in mind if you do mess with these things. Try and put these things back in place. And if you are messing with a hot rod or a race car or something custom, try to think about thermal failure. Try to minimize how close any of this can get to the exhaust or the turbocharger or anything hot, and try to think about where you could put some blankets or some coatings or some coverings to try and minimize the opportunity for failure in that way. Now, I got some real world examples for you guys, and I included these tonight because these are some pictures that I've taken over the past couple of weeks, and I thought you'd enjoy them. So this one right here was on a customer's Infiniti. The complaint was that the power seats, power mirrors, and the telescoping steering wheel didn't work. And it would have been really easy to go in and just throw parts at it, but that's not how we operate here. So in doing a lot of electrical diagnosis, I found that there was a module that controlled all three of those things. And it was actually the auto drive position module. And it's a module that when you get into the car and depending on what fob you have, the seats, the steering wheel, and the mirrors would all adjust automatically. Some of you guys probably have that feature on your cars, the memory seat module, that sort of thing. Well, the problem was, as you can see, corrosion from moisture had gotten into this connector and actually rotted off 5 of these pins. I don't know if you can see that on your screen. This connector is located way up under the dash, way up on top of the steering column, and a leaking windshield or sunroof, I'm not sure which of those were actually leaking, allowed water to drip on the top of this connector and rot these pins off. So I could have replaced the module, replaced the seat motor, replaced the switch. I could have replaced a whole bunch of components that would not have fixed this car. Ultimately ended up being the corrosion in this connector that rotted these pins off. That was the problem. Another good example, this was on a GM truck, and again, I hope you guys can see this on your screen, but this is on top of the transmission. The truck came in and complained that it would not shift. When it did shift, it shifted extremely hard. They had already put a valve body in it. They had already replaced the transmission control module. And this is one of those examples where, it comes to me after somebody has already spent a bunch of money trying to fix this problem. And after doing some digging, I found this brake on top of the transmission. And you can see that wire is in 2 pieces. I hope you can see that anyway. And so they could have saved themselves, who knows how much time and money by just finding the root cause of the problem. And the root cause of the problem was actually the supply wire to the pressure control solenoid inside the valve body. But once I fixed that, truck shifted great. So another good example of wire fatigue. This wiring harness was actually routed inside there and made an L. And right where it made the L, from vibration over time, that wire actually vibrated until it broke in half. And you see that a lot in door jams too. All right. David, I like your comment, buddy. Oh, hey, Russell, what's up? Hey, how you doing, buddy? Yeah. Yeah, my memory seat's the same way, David. This is another example. This one, I forget what kind of car this was on, but we ended up having a problem where it wouldn't start. And, they wouldn't turn the starter over, wouldn't do anything. And what I ended up finding was one of the main power supply wires to the ignition switch ran from the fuse box, across the firewall and out to the ignition switch and to the rest of the car. it ran right by the AC evaporator, or receiver dryer rather. And right down here, you can see this rust spot. And that rust spot is where these wires had been rubbing for a long time. And eventually, it actually rubbed all the way through that wire. And so this is an example of why it's important to put that sheathing and put the wires back into there. You can see this, it's broken right here. That's the clip that the loom used to be in. There's another one on the other side. So somebody had been working on this car and broke these clips, didn't put the loom back on it. And over time, you can see where it just rubbed and rubbed and rubbed until it rubbed right through that wire and the car ended up not starting. And these are the type of things that can drive you crazy because, how do you if you're going out to start your car in the morning and it don't start, is that going to be the first place you look? Is your AC receiver dryer to see if the wiring harness had rubbed through it? Probably not. So this is one of those examples why it's really important to always put those things back in. If you can't put them back in the factory loom, at least try to do your best to pull them away from anything that they may rub on or touch, and put loom or some sort of protection back over the wire, even if it is just electrical tape, just something. And here we go. This is another good one right here. So this was on a Chevy Cobalt, I think, or maybe a Cruze. I think it was a Cruze. This is another example. The car comes to me, and it starts and idles, but you can't give it any throttle. You hit the throttle, nothing happens. Car won't do anything. Doesn't respond at all. You see this a lot with modern cars with TAC modules, with electronic throttle bodies. If the car detects a fault, you'll see it go into a reduced power or a limp mode, where the car will start and run, but you just have no throttle control or very limited. In this case, this is another example of it rubbing through. And on this one, this was on a GM, which are notorious for the looms just deteriorating. You just touch the loom and it turns to powder in your hand because I don't know what they used on them. But mid 2000s to late 2000s GMs are really notorious for this, and this is something you can be on the lookout for. What happened was actually the loom had deteriorated at some point during the car's life, and this throttle sensor wire, this is actually the 5-volt reference wire going to the throttle body, had actually rubbed through and was touching on this bracket, and so the car just saw that as a short. It just saw it as a failure, but because that was a low current wire, it didn't blow a fuse. There wasn't enough current in this to actually blow a fuse. This was actually a signal wire. So all the PCM saw was that signal wire was grounded, and it said, I'm not giving you anything. And it didn't give us any throttle control at all. But this is another example, you pull the car in, you pull the code, you start doing your proper diagnosis, and you can find these little things that, while they may take hours to find sometimes, generally there's not a component failure involved. And this is another example of why it's always important to keep these looms wrapped and routed away from anything that they may be able to touch. This is a really good one. I hope you guys can see this coming through on the screen here. But we've got the trifecta here. We got Scotch blocks. We got wire nuts. How many? 1, 2, 3, 4, 5, 6, 7, 8 at least wire nuts. We got some look like proper splices wrapped in there. I don't know how many different people did this. There's obviously no loom. There's no protection. You can see where it was cut back here. This was behind the AC control panel on a customer's car, and it was a disaster. And what I actually ended up finding was that one of these wires had pulled out of one of these wire nuts and was touching the ground. It was actually blowing fuses. So that's the after. The wire's all loomed up, it's zip tied properly. The connectors are in their proper place. You see I added some protection down here where it runs across the bottom of the control panel. So that is a good example of, even though I only changed one wire to fix the car, it took a lot of time to actually do this correctly and cut all that stuff out and actually put it back the way that it should be to try and mitigate the chances of something like that happening again. This is a good one. This is on a friend of mine's Honda. As a matter of fact, this is a pretty common Honda failure. This is the main relay on Honda. It's a black box underneath the dash of the car. And this is a main relay, so this controls PCM, the fuel pump, a lot of other high current things. And you can see where the board actually corroded and actually separated from the circuit board. So this is one of those examples where, just looking at it, you may or may not think there's anything wrong with it, but through electrical testing, you could actually see that wasn't carrying a load. But that's a pretty common failure also. So this is another example of corrosion causing a problem, even though you couldn't see it. This was inside of a black plastic box under the dash. So definitely want to keep that in mind too. So when I say corrosion can be a bad deal, it can be a really bad deal and very hard to find as well. All right, the last thing I'm going to talk about real quick so we can end this hopefully a little bit on time is overheat causes. So this is an actual picture I took behind our shop of our junk radiator pile. These get sent off to be recycled, but that's a lot of radiators and AC condensers, so these things do fail. But overheated can be caused by a number of things, and one of the most common reasons is insufficient cooling. If you don't have enough coolant in the car, chances are it's going to overheat. The reason that they usually don't have enough coolant is because there's a leak somewhere. So this is another one of those situations where, you could fill it up with coolant and it'll stop overheating, but why was it low on coolant to start with? That's where you need to start asking questions and start doing a little diagnosing. Failed cooling fan or circuit. We talked about that with the high current DC motors. You see, the fans quit working for any number of reasons we talked about: corrosion, failed connector, blown fuse, whatever the case. The car will overheat. The pump drive failure, whatever drives the pump. A lot of vehicles are timing belt driven, timing chain driven. Most of them are driven off the front crank pulley on the accessory belt. Some are driven off the back of the cam, on a separate belt altogether. Looking at you, North Star. But yeah, any sort of failure in the drive can cause an overheat. Thermostat, of course, is an obvious one. If thermostat sticks shut, again, you can have an overheat situation. But that's another situation where you want to ask yourself, what made this thing stick? Is there a lot of rust and corrosion inside the cooling system? Have you been running the wrong kind of coolant? Or did it just fatigue failure? Did it just failure over so many thermal cycles? Restriction in the radiator, again, it's another one of those things where you could replace the radiator and it'll fix the car. But you want to ask yourself, where did that restriction come from? How did you get rust, dirt, mud, rocks, who knows what, inside that radiator to cause that problem? And then retarded ignition timing is one that a lot of people don't think about, but not so much of a problem anymore with computer controlled timing. But on older cars that had a distributor or they had a separate ignition module, anything that you could control the timing with, if the timing were too far retarded, you'd get extremely high cooling temperatures, and so you could replace all of this and it would still overheat because the ignition timing was off. So usually there would be some other symptoms there too, like lack of power, knocking or something like that. But and I just included this real quick. I'm not going to spend a lot of time on this, but we talked earlier about two different types of metals and how they expand and contract at different rates. And we talked about overheating just now. Well, this is where those two things culminate. If you have a car that's been overheated, or it's been, some cars are more sensitive to it than others, but most modern cars use an iron block and an aluminum head. And when you get those temperatures way beyond what they were designed to handle in an overheat situation, they expand even more so than they normally would, and that usually opens up for head gasket failure. I'd probably say 80 to 90% of the head gasket failures I've ever experienced as a technician have been due to the car being overheated at some point. And it doesn't have to happen all at once. You could overheat it one good time and let it cool down, and fill it back up with coolant and fix whatever made it overheat. And you might be good for a while, but chances are that aluminum it expanded to a point where maybe it cracked, or maybe it allowed a weak point in the gasket, or maybe it stretched one of the bolts or anything like that. So it's very, very important that after the vehicle is overheated, again, this is one of those things where the technician may come out to you and say, hey, we've got it cooling, but there may be another problem. And this is usually what you see. Or, you take it to him and say, hey, I overheated this thing until it shut off, or I overheated it, and drove it home anyway. He may tell you, well, now you need a head gasket, or you need an engine. In most cases, it's cheaper to put an engine in them than it is to replace the head gasket. And in most cases nowadays anyway. But yeah, that's just something to think about. This is where you see that thermal expansion and the overheating situation that's where it really culminates a lot of times, is the difference between the block and the cylinder head, which could cause a failure in any one of these ways. There's 7 ways that shows it here, but basically if that head moves off the block for any reason, it's going to be a bad time. Alan Anderson, I see you're on here. Good info on the leaking windshield. Yeah, that one was a tough find, man. So yeah, be on the lookout for that. Ford trucks also, they're pretty notorious for that. The Ford trucks that have the fuse panel and the passenger side kick panel, They're really bad for windshield leaks. They drip down on top of that fuse panel, and they cause all sorts of weird problems. Cadillac SRXs, Equinoxes, those things. The rear hatch leaks on those a lot. There's a lot of modules back there in the wheel well, the spare tire well. They cause all kinds of problems. Mercedes is another one. They have back windows that leak or sunroofs that leak, and they got a lot of modules underneath the back seat, and that's where that water likes to pull up and cause all sorts of problems. So yeah, definitely. If you do end up finding a corrosion issue, or you do end up finding something like that, try and be on the lookout for why that thing failed. Anybody else got any comments or questions or anything while we're still live here? I love that you guys kind of got some feedback tonight, so I definitely appreciate that. I hope you keep it up, and if you guys are still with me, let me know. But that's all I got for you tonight. I hope this made sense to you. If it didn't, feel free to ask questions, like I say every time. And also, if you have any prayer requests or prayer needs, you can post them up. If you're not comfortable with that, you can send a private message or go to tanglewoodchurch.com. They've got some full-time prayer warriors on there that would love to hear from you. So, reach out to them and connect. But other than that, I think we'll close this one out. I hope everybody had a great day. Hope you enjoyed the weather. Hope you guys are all at work, or if not, we'll be back to work soon. And if there's nothing else, then I'll pray and we'll get out of here. All right. Father, thank you for this time, and thank you for these people. Father, I pray that you be with each and every one of them as they deal with this crisis in their own way, Father. And I would pray that you would be with each and every one of them, including myself, in seeing your strength in our weakness, Father. When we go through trials and tribulations, Father, that we would count that as a blessing, Father, that we would be able to use that to glorify you and see your strength in everything. And Father, we just pray for safety until we meet again. It's in Jesus' name. Amen. Amen. All right, guys. Well, until next week, I will see you next time. And like I said, you can see it on YouTube, Facebook, and definitely drop me a line. And if there's any sort of subjects you want to see covered, any specific things, I definitely need some more ideas for courses. So definitely drop me a line and let me know if there's anything you'd like to see. Until next time, thank you, guys.